Lead-acid batteries have been around since the 19th century and are in fact the first ever rechargeable batteries known to mankind. It was only after the lead-acid battery that the nickel-metal-cadmium battery was developed. However, due to environmental concerns caused by the cadmium electrode, it was taken over by the nickel-metal hydride battery in the late 20th century. And shortly after this, the lithium-ion battery was introduced in the market. Despite the lead-acid battery no longer being used as the primary source of power in EVs due to its poor capacity and efficiency, the nickel-metal hydrides are still used in hybrid EVs like the Toyota Prius and all-electric vehicles like the Toyota RAV4 EV. They are either used on their own or in combination with lithium-ion batteries. In this video, you will learn about the construction and working of the lead-acid and nickel-metal hydride batteries. First off is the lead-acid battery, which is primarily used in IC engine cars to start the engine. Lead-acid batteries are used in situations that require intermittent supplies of electricity, and they are preferred for their inexpensive yet safe and reliable nature. Electrical energy is produced by the lead-acid battery when a chemical reaction takes place between the two electrodes. One electrode is made of pure lead, which is spongy, and the other is made of lead peroxide, which is rigid. These electrodes are dipped in a sulfuric acid solution, which acts as the electrolyte. If these two electrodes come in contact with each other, they may short-circuit the system. To prevent this, separators made of rubber, wood, or glass are placed in between the electrodes for insulation. During the discharge phase, lead peroxide acts as an anode and lead as a cathode. When the circuit is closed, the acid molecules split into positively charged hydrogen ions and negatively charged sulfate ions. The hydrogen ions, which are missing an electron, move towards the lead peroxide to gain electrons and become neutral. This electrode now becomes positively charged as it has lost electrons to the hydrogen ions. When this happens, the negatively charged sulfate ions in the electrolyte move towards the lead and transfer their electrons to the plate. As a result of these reactions, lead sulfate is formed on both the anode and cathode, leaving white deposits. So, if you pull out the electrodes and find white deposits on them, you will know that the battery was used. Now there is an imbalance of charges at the two electrodes. To neutralize the charges, the excessive negative charges on the lead plate move along the external circuit to the lead peroxide plate, thus generating electricity. Reactions that happen during the recharge phase are the exact opposite of those that happen during the discharge phase. When recharging the lead-acid battery, the connections are reversed, and this causes the hydrogen and sulfate atoms to get ionized again. They move towards the opposite electrodes, and the battery is ready to supply electricity. Lead-acid batteries are classified as either flooded or sealed batteries. Flooded lead-acid batteries are widely used in the automotive industry today. They are called flooded batteries because the acidic electrolyte solution is free to flow around the battery casing. Oxygen and hydrogen gases produced during the discharge phase are released via openings in the casing. Since there's a chance that the acid can leak from these openings, they have to be positioned strategically. Moreover, water can evaporate from the electrolyte solution due to the heat generated from the chemical reactions. This is why distilled water needs to be refilled in the battery at regular intervals. Sealed lead-acid batteries, on the other hand, have a completely enclosed casing. The electrolyte is in a gel state rather than a liquid state to prevent leakages. The oxygen and hydrogen gases produced combine to form water. This water is used to keep the gel from drying up. However, a cleverly designed vent is installed for the excess hydrogen to be released. If this hydrogen gets trapped within the housing, it may ignite due to high temperatures. And for this very reason, it is called a valve-regulated lead-acid battery, or VRLA. Lead-acid batteries lose out to lithium-ion batteries because of their poor performance in cold temperatures, low energy density, lifespan, and range. It is these very limitations that put the nickel metal hydride battery in the lead in the automobile industry. Nickel metal hydrides have a cylindrical casing with a metal hydride anode on one side, a nickel cathode on the other side, and a potassium hydroxide electrolyte. When the anode and cathode are dipped in the electrolyte solution, electrons are lost and gained at the respective electrodes via the external circuit. During the recharge phase, the reactions are reversed, and the charges get restored when the ions recombine to form the metal hydride and nickel. But why do some car manufacturers still opt for the nickel metal hydride battery when the lithium-ion battery is around? Well, when compared to the lithium-ion battery, the nickel metal hydride battery can actually withstand extreme ranges of weather conditions, making it all the more resilient. So there you have it, the basics of the lead-acid and nickel metal hydride batteries. While they may be considered archaic battery technologies, they are still around and serving their purpose in the EV industry.